With the ideas of remembering the results, we see that memoization is simply wishful thinking. If the answer is not there, just compute it. There is no fixed order to do the computation. It just assumes it is there. If not, recursively compute it. Dynamic programming is similar but different. This particular name does not mean anything, just a term that sounds sophisticated for the funding purposes when it was first invented. Compared to memoization, this video shows a more structural way of remembering results and to compute the next result. In general, it is an approach to solve a problem by combining the solutions of smaller problems. A quick comparison with memoization before we start with dynamic programming, so that you can keep in mind when studying dynamic programming. Both memoization and dynamic program are filling up entries in a table. For the case of memoization, an entry in a table is filled up in no particular order. But for dynamic programming, it is filled up in a systematic way. For memoization, because the table is accessed in no particular order, it has to be supported by a dictionary for fast access. On the other hand, dynamic programming is accessed in a systematic manner and thus can use a simple list to keep the answers. In some way, memoization is a top-down approach, while dynamic programming is a bottom-up approach. With these notes, we are now ready to see the same three examples using dynamic programming to solve them. The first example is the familiar Fibonacci number. Here is the memoization. And by definition, Fibonacci number n is simply the sum of the previous two numbers. So it is easy to convert from a recursion into an iterative. And we simply calculate from the first two base cases to the third one and so on. So here's the code. The table is initialized with all zeros. And the first one, it's assigned to 1. So the zeros and 1. So these two are correct in the table. The rest of the number will simply be the sum of the previous two numbers. So you're just simply having a for loop to complete the task. And then you return the last one in the table. That is your answer. So the table is filled in from left to right as in the for loop. And actually you can see that we don't need the table also, as we only need the previous two numbers. So we could have simply used two variables to keep track of that two numbers instead of a table. In any case, we still show you the use of a 1D table just to illustrate this simplest dynamic programming in keeping track of numbers along the way. The next example is n choose k. It's memoization solution as we saw before. Looking at the recursive formula, choose n-1, k plus choose n-1, k-1 to be the result. We actually treat the n as the row and k as the column. So if you say that, then n-1 is the previous row and the same column k, and n-1 is the previous row and k-1 is the previous column. So from this recursive formula, we see that we need the row before at the same column and the row before with the column before. If we can systematically go through row by row, we can always fill in an entry as each row before has been completed to provide the numbers we wanted. So we're going to see a row by row filling in of a table of size n times k. By the way, doing it column by column also possible for this example, but we shall see only the row by row solution. This is again our memoization solution. This is the table that computed. There are n plus 1 rows and k plus 1 columns. The first row is row 0 and the first column is column 0. So our dynamic programming solution is to compute the same table and to return the final answer here, 70, for n equal to 8 and k equal to 4. Here's an example. To get 3, it's from the previous row, previous column, and the same column. Here's another example. To get 35, we needed the previous row, 15 and 20 to add up to be 35. Here is the dynamic programming solution with the double loop to fill in the table, and the space is n times k and the time is also n times k. The tricky parts of the code are on two things. 1. Get the initialization right, and 2. Get the indices right in filling in the table. On the first point, be careful with aliasing that we could make mistake with dealing with lists. We want each row to be itself and not an alias of another row, so that in changing one entry in a row, we don't accidentally change the entry in another row. So notice we use row.copy so that we have distinct copies for all the rows. On the second point, we need to make sure that the double for loop of I means row and j means column and use I and j correctly. With these 2 points taken care of, we have a correct code, and the time and space complexity are O of n times k. Let's spend a bit of time to go through the codes for a better impression on what's going on. We use n equal to 8, k equal to 4 for our illustration here. The row has 5 entries for k equal to 4. This is one extra for the first column, which is column 0. With one row, we now copy it to form 9 rows in the table with n equal to 8. Again, one extra rows to 8 because there's this row 0 here. And for this row, the first entry as a 1 is correct because we have no items and we want to choose no item. There is exactly one way. But for the other entry, there should be zeros rather than 1. So we have this for loop to do that, to set them to 0. With row 0 correct, we next fix up the row 1 with 1 0 0 0 because this 1 comes from the sum of 1 plus 0 to get 1. This 0 is because of this 0 plus 0 to give 0. This 0 is the same and this 0 is the same. And this calculation is based on this table ij. It's equal to table I minus 1, the previous row, and the previous column, plus the previous row, the same column. So here we show I equal to 1, this row is fixed up. Next, we show I equal to 2, this second row is fixed up. These 2 come from 1 plus 1 to 2, 1 plus 0 is 1, and the rest are zeros. And fast forward, we see that all these other rows are filled up. We have the answer 70 to return. Our last example. Can we adopt a dynamic programming approach for solving this chocolate packing problem? Yes, we can do it for this case too. The difficulty is at the design of the packing table. We know an entry we get has to be the optimal choice for a list of given chocolates with a given weight limit. This is clear, but how to see what is smaller problems to use to combine into solution of bigger problem? And on the chocolate to use is then naturally from no chocolate to include 1 chocolate and then 2 chocolate and so on. With these 2 points, our challenge is resolved to be a 2D table, and we use row to be each weight limit and column to be no chocolate to 1 chocolate and then to 2 chocolates and so on. First, we know that when we have no chocolate, the answer is simply empty set. When there are k types of chocolates, then the answer is the better version of either the kth chocolate plus the optimal choice with remaining k minus 1 types of chocolate and reduced weight limit, or optimal choice with remaining k minus 1 types of chocolate and current weight limit. That is, the new kth chocolate is not used in this choice. Here is the table. We have row 0, row 1, row 2, etc. These are all the weight limit of 0, weight limit of 1, and so on. When there's no chocolate, this column. When there's 1 chocolate, we simply call it A with weight 4 and rating of 2. Then this is a column with 2 chocolates now, added with the B with weight 5 and rating 3. Then with another chocolate, C with weight 3 and rating 2, etc. if you have more chocolates. Then this is the table. How do we have all these values here? So the first column is simply when you have no chocolate, whatever weight limit you have, you don't have any chocolate to put into the box. So the optimal here is just simply empty set. When you have 1 chocolate and your weight limit is 0, you can't put the chocolate into the box, so it's still an empty box. Likewise, if you have 2, you still empty, with 3 also empty. So this column 0 and row 0 have optimal solution of an empty set. This is exactly our observation in the previous slide. As in the previous slide, the other entries are coming from these 2 options. And these 2 options help to fill in the rest of the entry here in green. For example, for us to get this particular entry B with C in the box, for row 8, weight limit of 8 with 3 chocolates, with the new chocolate C of weight 3 and rating 2, we will look at the weight 8 minus the weight of C to get weight 5, referring to this box plus the new chocolate with rating then now 3 plus 2 is 5, compared with this previous box without the chocolate C, which is A and A of rating 2 plus 2, 4. So B plus C is a better choice than AA. Therefore, the optimal result here is B and C in the box. We will leave it as a homework for you to try out the full code before you refer to the PPT with the solutions. With this, we finish our discussion on dynamic programming. You can find many more sophisticated examples on dynamic programming in the web.